Consider this. Everything your computer does, from playing a video to sending an email, boils down to tiny little switches. And I mean tiny. Millions, even billions of them all working together. These switches are called transistors, and they're the most basic building block of all modern electronics. Think of a transistor like a simple light switch on your wall. When you flip the switch on, electricity flows, and the light turns on. When you flip it off, the flow of electricity stops, and the light goes dark. A transistor does the exact same thing, but instead of your finger flipping the switch, it uses a small electrical signal to do the job. Now, in the world of computers, we don't usually say on and off. We use numbers. We represent the on state with a 1 and the off state with a 0. This is the binary system, the fundamental language of all computers. So when a transistor receives a small electrical signal, a 1, it turns on and lets a bigger current pass through it. If it doesn't receive that signal, a 0, it stays off and the current is blocked. This simple on-off 1 or 0 action is the key to everything. It allows us to control the flow of information, which is just electricity, in incredibly precise ways. Imagine a gatekeeper standing at a gate. If the gatekeeper gets a secret password, our small electrical signal or a 1, they open the gate and let the crowd, which is the bigger electrical current, rush through. If they don't get the password, a 0, the gate stays firmly shut and nobody gets past. Transistors are our microscopic gatekeepers, controlling the flow of electrical signals billions of times every single second. This isn't just a clever trick. It's the principle that allows a machine to think by making simple, logical decisions based on electrical inputs. These tiny switches are made from silicon, a material that's a semiconductor. That means it's not quite a conductor that lets electricity flow freely, and it's not quite an insulator that blocks it completely. It's somewhere in between, which makes it perfect for this job. By applying a small charge to a part of the silicon, we can change its properties and make it act like a conductor or an insulator. This is how the transistor flips. This ability to switch between two states, an on and an off, is what makes the digital revolution possible. Every single calculation is just a bunch of these switches flipping. Now, one transistor is neat, but it can't do much on its own. The real magic happens when we start connecting them together. Think of it like building with Lego bricks. One brick is just a brick, but when you snap a few together, you can create something new. When we combine a few transistors in specific patterns, we create something called a logic gate. These gates are the next step up in our computer's brain. They take one or more inputs, our ones and zeros, and produce a single output based on a specific rule. It's like a little decision-making machine. Let's look at a few basic gates. First up is the NOT gate. It's the simplest of all and is made with just one transistor. Its job is to be contrary. If you give it a 1, it spits out a 0. If you give it a 0, it spits out a 1. It always gives you the opposite of what you put in. Then there's the AND gate. Imagine a door with two locks. To open the door, get a 1 as output, you need to unlock both lock 1 and lock 2. If only one lock is undone, or neither is, the door stays shut and you get a 0. An AND gate needs two inputs to be 1 for its output to be 1. Another important gate is the OR gate. Think of a door with two separate handles. You can open the door by using handle 1 or handle 2. As long as at least one of the handles is used, the door will open. The OR gate works the same way. If either of its inputs is a 1, or if both are 1, its output will be a 1. The only way to get a 0 from an OR gate is if both of its inputs are 0. These simple rules, NOT and OR, are the foundation of all computer logic. They allow the computer to compare information and make choices. By arranging transistors in these specific ways, we create physical circuits that obey these logical rules. The flow of electricity is guided through the transistors, and depending on which inputs are on, the final output path will either have current or not. For an AND gate, the transistors are wired in a series, so the current must pass through both to get to the end. For an OR gate, they're wired in parallel, giving the current two different paths it can take. It's all about creatively controlling the flow of electrons to get the answers we want. Okay, so we have logic gates that can make simple decisions. That's cool, but how do we get from and OR to doing math? By combining our gates, of course. Let's build a circuit that can add two binary digits. This little contraption is called a half adder. It's made from one AND gate and another special gate called an XOR gate, which stands for exclusive OR. The XOR gate is like an OR gate, but it only outputs a 1 if one input or the other is 1, but not both. It's exclusive. A half adder takes two inputs, let's call them A and B, and gives two outputs, a sum and a carry. Think about adding 1 plus 1 in grade school. The answer is 2, right? In binary, that's written as 1, 0. The 0 is our sum, and the 1 is what we carry over to the next column. The half adder does exactly this. The XOR gate calculates the sum. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 is 0. The AND gate calculates the carry. 1 plus 1 gives a carry of 1. All other combinations give 0. It's simple binary addition. But wait, what if we're adding bigger numbers and already have a carry from the previous column? A half adder isn't enough. We need a full adder. A full adder is a bit more complex. It's essentially made of 2 half adders and an OR gate. It has 3 inputs, A, B, and a carry-in from the previous column. It still gives us 2 outputs, a sum and a carry-out. This allows us to chain them together, like a line of people passing buckets of water. Each full adder does 1 column of addition and passes any carryover to the next one in line. Now, let's put it all together. The part of the computer's processor that does all the math and logic is called the Arithmetic Logic Unit, or ALU. The ALU is like the calculator part of the CPU's brain. It contains circuits like our adders to perform addition. It also has circuits to do subtraction, which is just a clever form of addition, as well as circuits that perform the logical operations we learned about, and, organ, and not. When the CPU needs to calculate something, it sends the numbers and the command, like add or compare, to the ALU, which uses its specialized circuits to get the job done almost instantly. So, we've gone from a single switch to a circuit that can add numbers. The final step is one of scale. A single full adder can add 1 column of binary digits. But our computers work with numbers that are 64 digits long. To add 2 64-bit numbers, a CPU simply lines up 64 full adders, 1 for each bit. The carryout from the first adder becomes the carry-in for the second, and so on, all the way down the line. It's a cascade of simple operations happening at lightning speed, and this is just for addition. The ALU has other sections dedicated to all its other functions. The real power of a modern central processing unit, or CPU, comes from the sheer number of transistors packed inside it. We're not talking about a few dozen or even a few thousand. We're talking about billions. Today is September 7th, 2025, and the processors in our newest devices contain tens of billions of these microscopic switches. Each one is smaller than a virus. All these transistors are arranged into an incredibly complex city of logic gates, adders, memory registers, and control units, all etched onto a single chip of silicon no bigger than your thumbnail. This immense collection of transistors allows a CPU to do many things at once. While the ALU is adding some numbers, other parts of the CPU are fetching the next instruction, decoding it, and getting the data ready. It's a highly efficient assembly line where billions of workers, the transistors, are all flipping on and off in a perfectly choreographed dance, guided by the rhythm of the computer's internal clock. This clock signal synchronizes everything, ensuring that operations happen in the right order, billions of times per second. So the next time you watch a high-definition movie, play a graphically intense video game, or even just move your mouse across the screen, take a moment to consider what's happening. Billions of tiny, silent switches are flipping from 0 to 1 and back again. They are performing trillions of simple calculations every second, all starting with the basic logic of AND, ORGAN, and NOT. From a single transistor acting as a simple switch to the supercomputer in your pocket, it's all built on these simple, powerful principles. Science is amazing,